let's start with the next speaker, who is Hossein, and he will be talking to us about hybrid quantum variational algorithm for simulating open quantum systems with near-term devices.
Hi all, I hope you are safe and happy. My name is Hossein Davoodi Yeganeh from University of Tabriz, Iran. My talk is about the hybrid quantum variational algorithm for simulating the open quantum system on a near-term device. I want to talk about the review quantum computing in brief, a principle of hybrid quantum classical algorithm, and the simulation of dynamic of open quantum system. We know that classical computers have a fundamental limit due exponential growth of variable classical computation method fail to simulate system with complex many-body interaction. And we know that quantum computers have many applications in the many areas such as machine learning, supply chain optimization, robotic, and material science, and so on. The first idea to proposed by the Feynman to simulation a quantum system by a quantum computer. Feynman proposed this idea to use a quantum system to simulate other quantum system. If we know that it is a quantum computers. So quantum computer consists of the quantum algorithm. A small area classical algorithm is a finite sequence of instruction or step by step for solving a problem where each step can be performed on the classical computer. In a quantum algorithm, we have a finite sequence of instruction, step by step. That step performed on the quantum computer. I mean, you can perform the quantum algorithm use a model beginning the quantum circuit model of computation. Quantum algorithm usually use the properties of the mechanical quantum, such as the quantum superposition or quantum entanglement. That is the main properties of the quantum algorithms. But many quantum algorithms have the Yeganeh resource requirement when compared to the available today. We have some and many of qubits, but we can't implement all quantum algorithms. To address this discrepancy, quantum classical algorithm was introduced. In hybrid quantum classical algorithm require a classical computer and the quantum computer to communicate and work cooperatively. You can see schematic of hybrid quantum classical algorithm in this picture. State preparation and the measurement performed on the quantum computer and the classical computer update the variational parameters by using optimization and solving a differential equation and so on. Note that hybrid quantum classical algorithm can be implemented on the noisy intermediate scale quantum NISQ technology. Noisy refers to that the fact device will be disrupted by happening the environment, for instance, a small change in temperature or electric field, and so on, cause the decoherency for our system. So we need to be able to perform error correction. Intermediate scale refers to the fact the number of qubits will most likely be limited for a few hundred or perhaps a few thousand. In the many paper or lecture, the term NISQ is often used interchangeably, but near term when speaking on the quantum computing because the device will develop in the next few years. And note that we lack error correction, mean we don't need to perform error correction in the NISQ technology. So we can use the variational algorithm to simulate and simulated system or variational or eigensolver and optimization problem. Example of HQC algorithm is a variational quantum eigensolver. Variational quantum eigensolver, VQE, is a hybrid quantum classical algorithm designed to use both the quantum and the classical resource to find the variational solution to eigenvalue and optimization problem not accessible to traditional classical computer. This algorithm introduced in 2014 by McLachlan and their colleague. You can see schematic of this algorithm in here. Outline of this algorithm can be summarized as a prepared state psi theta or rho theta is a parameterization state. Measure the exception value Hamiltonian. Use a classical nonlinear optimization such as a Nelder-Med simplex method or other to determine new value of theta and decrease the h. And in step 4, iterate this producer until converge the value of energy. This is a famous of the hybrid algorithm. VQE you can see in the many lecture and the paper about this algorithm. So we use this algorithm to simulate the dynamic of open quantum system. As we know, real quantum systems are not isolated from the past, but always interact with the environment. And due to type of interaction and the strength of coupling between the environment and the system, the dynamic of open system can be divided into two categories: Markovian and non-Markovian. Here we consider Markovian dynamic or memoryless. In a Markovian regime, the master equation can be described the dynamic of the open quantum system. Can be described as a rho dot equal to L on rho. You can see here L on rho equal to the master equation in the Lindblad form. And rho is a density matrix by this form. So the basic idea of simulation we used in our paper is that given that a state as a current time t determined, the state t plus delta t according to the time depends a variational principle TDVP, which indicates the Frobenius norm must be minimized. Here you can see the Frobenius norm rho dot minus L rho. In the stationary condition, this equation can be considered as a trace delta rho dot minus L rho equals and delta rho equal this equation. We can use this Frobenius norm to achieve to obtain a equation of motion for this for open quantum system. We use this variational principle trace this equation we can use, and the density matrix we can obtain this equation. You can see this B dot equal to the so on here, where S is a overlap matrix, tau is a psi k overlap psi dot C, L KL is a matrix element of the L rho. We can use a trace this equation and obtain this after some calculation. We can derive and obtain this equation. This equations sigma L of beta equals 0. Sorry. So by this calculation is a hard. I can say is a complicated, and you can see this equation of motions b dot and z dot. Here we consider a parametric state psi k tt is a mapped to the parameter z. So psi dot equal this equation, s equal this equation, and tau is the formula. You can see this. So we can obtain a C, Y, L by this definition and implement this coefficient on the quantum computer. Note that in CYL, we have an overlap term. You can use the Hadamard test or swap test to calculate them and use a quantum computer for calculation B dot and Z dot. You can see here schematic of our algorithm to use the simulation of dynamic of open quantum system, preparation initial state, and calculate the operator L, overlap matrix tau, matrix C, vector Y, and classical computer solve the equation of motion. I mean B dot and Z dot, and product the new parameter set. For example, we can use this algorithm for simulation dephasing noise. You can, this dephasing noise can be described by this master equation rho dot H is a Hamiltonian of system equal to the sigma z. Psi is a superposition of 0 and 1, and rho c, rho 0 initial rho is a ket psi in rise. In HQ algorithm, we can consider parameterizing state psi 1 and psi 2 in this form. We can see and use this definition. You can use a C, K, and L and solve a master equation B dot and Z dot. We can here plot the exception value of sigma x is a Pauli matrix. In the time, you can analytical solution and the variational solution is the agreement with him, and you can see our algorithm have a good performance in to solve a equation. In brief, we use a novel quantum gate model. We have developed HQC algorithm in the near-term quantum resource to simulate open quantum system dynamics. Also, in future, we will extend this result to the non-Markovian dynamic of open quantum system. You can see more details about the calculation and the mathematical analysis for our algorithm here. That paper published it in G Journal of Physics, a mathematics math theoretical. And thanks for your attention of my talk.
All right, thank you. Thank you for the nice talk. So are there any questions? Okay, so I see that Andres has posted a question on Discord, so I'll just read it out. So if I understand correctly, in this scheme, noisy qubits are used to simulate noisy qubits. What are the resource requirements of this method? For example, how many noisy qubits are needed to simulate 10 noisy qubits or 100 noisy qubits?
Okay, we use the cost of the calculator C or L in our paper. Here we can we cannot consider this. You can see our paper for details about the cost of our algorithm and the qubit number and so on. Okay. I think I have a
question that is somewhat related, so I'll ask it quickly. So when we talk about these variational algorithms, so here the results that you have shown are when the qubits are themselves perfect. Is that correct?
Yes.
Okay, so what would happen if you introduce noise into the qubits that you're using for the simulation itself?
In this our paper, we don't consider the noise, and in next work we consider this and use a noise for this algorithm. Here we cannot consider this noise.
Okay. And when you talk about these unitaries, so in your slides you had this U, Z, alpha something.
Yes.
So what ansatz do you use some kind of ansatz to optimize? How do you parameterize the circuit?
You can see here here. Psi chi is a parameter state. U is a unitary operator such as a sigma z and so on. C, Y, and L is a computing the quantum computer. I mentioned this. This term is a overlap term, and we can calculate this term by using a quantum computer and Hadamard test or swap test. Also, we need a ancillary qubit to calculate this term. But all term can be computed on the quantum computer, and the unitary transformation can be applied this.
Okay.
Sorry, can I ask a question?
Yes, go ahead.
Okay, thanks, Hossein, for your talk. I'm curious to know how long does the calculation take? I mean, both the quantum part and the classical part. Is it long or short? I mean, you know.
The part that apply or implement on the quantum computer, this is a L, S, and tau and COK. And the classical computer solve equation of motions, B dot and Z dot.
Yeah, I know. I mean, how long? In especially classical computer to optimize your.
Okay. Here we not consider the time of the evolution of algorithm.
Okay.
Okay.
Okay, any other questions? All right, so thank you, Hossein, for the nice talk. So now we can move on to set up for the next speaker.
Thanks a lot. Have a good time.
Thank you.